Glycolysis breaks glucose apart and traps the energy that's released. It's an ancient way to trap energy, and it's conserved in everything from bacteria to spinach leaves to human beings. In humans, glucose is blood sugar, and this process happens in 10 steps. This video is about the first step. The first part of glycolysis transforms a molecule called alpha-glucose into another one called alpha-glucose-6-phosphate. This is what alpha-glucose looks like. An important landmark in alpha-glucose is this oxygen in this ring. There are 6 carbons in alpha-glucose, and they're numbered starting from the carbon to the right of the oxygen in this ring. So the first carbon would be there. Then you have carbon 2, 3, 4, 5, and 6. This reaction is going to transform alpha-glucose into a molecule called alpha-glucose-6-phosphate. And notice that the difference between these two molecules is a group that's on that carbon number 6. That group is the phosphate. Phosphate has 3 roles. So we're going to put a phosphate group on that carbon number 6, and that's going to accomplish 3 things. The first thing is that the phosphate is going to prevent glucose from being able to leave cells. There are channels in cell membranes that alpha-glucose can fit through, but alpha-glucose-6-phosphate cannot. So this phosphate group is going to prevent this glucose molecule from leaking out of cells. It's going to build up, and as it builds up, it's going to be more likely to react. As it builds up, it will fit inside the active site of enzymes, and that's another thing that this phosphate group is doing. So that's the second thing that the phosphate group is doing, is it helps to position this alpha-glucose molecule correctly in enzyme active sites. Finally, the third thing that the phosphate is going to be able to do is it'll allow us to trap energy that's released when we break apart glucose. Later in glycolysis, we're going to chop this glucose molecule into 2 pieces, and energy is going to be released. Having this phosphate here is going to allow us to trap that energy in a usable form, namely in the form of ATP. So, when you look at these 2 molecules, when you look at this transformation, most molecular stories are built out of 3 sort of storytelling elements. You can add something onto a molecule, you can subtract something from a molecule, or you can change the stability of a molecule so that it makes it easier to add or subtract something to it. When you compare these 2 molecules in particular, you'll notice the only difference between them is that phosphorus group. So we have to add that phosphorus group onto alpha-glucose. So we'll use that add storytelling element. The technical term for adding something, for how you add a group onto an organic molecule, a carbon molecule like this, is nucleophilic attack. Really, it's a fancy term for negative charge being attracted and sticking to something that's positively charged. A nucleophile is something that has a lot of negative charge. So you could identify it with your eye because it'll have either a full negative charge, a partial negative charge, a lone pair, or a pi bond. In alpha-glucose, on this 6th carbon, we have a partial negative charge. That oxygen is really electronegative, so it pulls electron density to itself and becomes slightly negative. So that is our nucleophile. Because the charge is only partial, that's what that lowercase delta, that sort of squiggly d, means. Because it's only a partial charge, it's not going to stick to positive charges as strongly. So although it is a nucleophile, we would call it a weak nucleophile. Weak nucleophiles will react more slowly. If we wanted this reaction to speed up and happen more efficiently, we could increase the charge on the nucleophile. Instead of having a partial negative charge, we could give it a full negative charge. That would make it a strong nucleophile, something that would stick to a positively charged group really well. So how can we go from a weak nucleophile with only a slight negative charge to a strong nucleophile with a full negative charge? When we do that, we change the stability of the molecule. The slight negative charge is more stable than a full negative charge. And to change stability, you use a storytelling element that's called proton transfer. The proton here is referring to a hydrogen atom. Hydrogen atoms have only 1 proton in their nucleus. A hydrogen atom is 1 proton with an electron going around it. If you remove the electron, then all you have is a proton. And so a proton refers to a hydrogen atom with a full positive charge. You can transfer hydrogen atoms with positive charge from one molecule to another. And as you do that, the charges on the molecule changes. Because the charge is changing, the stability changes. So we will do a proton transfer in this reaction. In the very first step, we're going to take our weak nucleophile, do a proton transfer, rip an H+ off of alpha-glucose, and get a strong nucleophile. So instead of having a partial negative charge, a weak nucleophile will have a strong nucleophile here with a full negative charge. And once we have a strong nucleophile, that can stick to or attack a positive species really efficiently. So we can do our nucleophilic attack. The positive species it's going to attack, the phosphorus in this group, is going to be attached to another molecule already. So to move from that other molecule to this one, it has to leave the other molecule. And so we'll use our third storytelling element, subtracting, to subtract the phosphorus from the molecule it's already on. The term for that storytelling element is loss of a leaving group. So we're going to remove a group from this phosphorus, and we're going to add this alpha-glucose oxygen onto it. When you remove one thing and add another thing in its place, you're really substituting one thing for another. And so this reaction is classified as a substitution. Because the two essential steps, removing something and adding another thing in its place, are happening at the same time, this is classified as an SN2 reaction, where the S stands for substitution, the N stands for the nucleophile that's doing the attacking to make the reaction happen, and the 2 stands for the two things that are happening at the same time, nucleophilic attack and loss of a leaving group. So this is conceptually how this reaction is going to work. We're going to do a proton transfer and then an SN2 reaction. Let's look at the specific details to make this happen. So we start with alpha-glucose. We know the first step is going to be a proton transfer where we'll change the stability of this molecule. And right now, there's only a slight negative charge on this oxygen. We have to remove an H+ from it in order to give it a full negative charge. And what can accept an H+ is a base. The base is going to come from an enzyme. And the enzyme that's used in this first step, or in this first part of glycolysis, is called hexokinase. There are various different forms of hexokinase in living things. You can always recognize that something is an enzyme that's speeding up the reaction because its name will end in ASE. A kinase, in particular, is an enzyme that transfers a phosphate group from one molecule to another, like we're going to be doing here. A hexokinase is an enzyme that transfers a phosphate group onto or off of a 6-carbon ring. That's what the hex or hexo prefix means here. So alpha-glucose has 6 carbons on it. That's the hexo. And we're going to be using this enzyme ultimately to put a phosphate group on here. So it's a kinase. So in the active site of this hexokinase, there is a base. And the base is hanging off of an amino acid called aspartate. So the 3-letter abbreviation for aspartate is ASP. But what we need to know is that this is going to act as a base. That base will be attracted to the slight positive charge on this hydrogen. Oxygen is much more electronegative than the hydrogen, so it's pulling electron density to itself. It becomes slightly negative, and the hydrogen becomes slightly positive. So when this glucose enters the active site of this enzyme, the negative charge on this aspartate is going to be attracted to the slight positive charge of that hydrogen, and it will rip it off of the molecule. The electrons that were holding on to the hydrogen will go to the most electronegative place nearby, and that's that oxygen. There's our proton transfer. The hydrogen moves onto the aspartate. So while the hydrogen was on the glucose, it's now going to move onto the aspartate. And the electrons that were going to that hydrogen will move onto the oxygen. So instead of having a slight negative charge, that oxygen will have a full negative charge as those electrons land entirely on that oxygen. So with that proton transfer, we've turned the oxygen on carbon number 6 of alpha-glucose from a weak nucleophile into a strong nucleophile. And now it can add onto another molecule in our second step. Again, the storytelling element that adds one molecule onto another is nucleophilic attack. So we have our strong nucleophile, it's ready to attack something. We want it to attack the phosphate, but that phosphate is already attached to another molecule. This other molecule is adenosine triphosphate, or ATP. The group on the right is the adenosine, and then you can see you have three phosphates, giving you the triphosphate of ATP. So in this case, we want to subtract this big clump on the right side of this molecule so that we're just attaching this one phosphorus group that we want on this oxygen. To subtract that, we're going to do loss of a leaving group. That's the storytelling element that we're going to use. So really, everything in green here is going to act like a gigantic leaving group that's going to leave that phosphorus on the far left. Because the nucleophilic attack and the loss of a leaving group are happening at the same time, this is going to be an SN2 reaction. The phosphorus that we want to be attacked is bonded to 4 different oxygens. All of those oxygens are pulling electron density away from the phosphorus, so this phosphorus is going to have a slight positive charge. And because the nucleophile has a negative charge, if it tries to get close to the positive charge on this phosphorus, the negative charges that are already here would repel it. So we have to pull those negative charges away from the phosphorus so that they don't repel the incoming nucleophile as much. You do that by having a magnesium present. The positive charge on the magnesium ion pulls electron density towards itself and away from the incoming nucleophile. So the nucleophile attacks that slightly positive phosphorus. The bond on the other side breaks. The electrons go to the most electronegative place nearby, in this case onto this oxygen. That's our loss of a leaving group. And so here, after this reaction happens, the phosphorus that was on the end of ATP ends up attaching to the oxygen on carbon number 6 of alpha-glucose. So now we have alpha-glucose-6-phosphate. And the leaving group is all by itself. If you look at the leaving group up close, you can see that there are only 2 phosphates here. And so now, instead of being adenosine triphosphate, this is adenosine diphosphate, where the di is representing the 2 phosphates on that. So in this first part of glycolysis, we've turned alpha-glucose to alpha-glucose-6-phosphate. We did that through sort of 2 steps. The first was a proton transfer. We used a hexokinase to rip an H+ off of the oxygen on carbon number 6 of alpha-glucose. That turned the slightly negative oxygen, which was a weak nucleophile, into a fully negative oxygen, which is a strong nucleophile. That could then do an SN2 reaction by attacking, doing nucleophilic attack on the phosphorus of ATP. ADP acts as a leaving group. And because you have nucleophilic attack and loss of a leaving group happening at the same time, this is classified as an SN2 reaction. The purpose, the overall, what we achieve in this first part of glycolysis is we put a phosphate group on that oxygen on carbon number 6 of alpha-glucose. So alpha-glucose turns into alpha-glucose-6-phosphate. And again, what that phosphate group does 3 things. The first thing it does is it prevents glucose from leaving cells. There are channels in plasma membranes that alpha-glucose can fit through. Alpha-glucose-6-phosphate does not fit through those channels. That means it builds up in the cytosol of cells and is more likely to enter the active site of the enzymes in future steps in glycolysis. As it builds up in the cytosol, it enters those active sites, and when it does, this phosphate group and the charges on it are going to help position alpha-glucose-6-phosphate in those active sites so that it reacts quickly. That's the second thing that we achieve by putting this phosphate group there. Finally, the third thing that this phosphate group achieves is later on in glycolysis, we're going to break glucose apart into 2 pieces, and that's going to release energy. And this phosphate group is going to allow us at that point to trap that energy in a usable form, namely as an ATP molecule. So that's the first part of glycolysis, turning alpha-glucose to alpha-glucose-6-phosphate.